In this video, we're solving problem 12.5.505.xp from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're told to consider the following. We're given y equals the hyperbolic sine of x, and I've written it here in terms of exponential functions as well. We're asked to find the points on the curve at which the curvature k is at a maximum. So we need to find the curvature, and then we need to maximize it. And this indicates that there are two x values where the curvature is at a maximum. There's going to be one with a smaller x value and one with a larger x value. Now this is what you'll see in WebAssign. You'll see an ordered pair xy, and they've got parentheses already typed in there and then a blank. So you have to enter the x and then the comma and then the appropriate y value. So you're going to do that for both of those. Those are the locations where the curvature is at maximum on this hyperbolic sine function. And then we're asked to find the limit of k as x goes to infinity, or the limit of the curvature as x gets really large. The question is the curvature approaching 0? Is the curvature approaching 5? What value is the curvature approaching? And we'll just evaluate the limit of that function in order to do that. Okay, so the first thing we need to do in order to answer part A is find the curvature function, and then we need to maximize it. So we go to our list of formulas for curvature, which we already derived in earlier videos, and we look for the one that's appropriate for the given function. Now we were given y as a function of x, so out of all of these, the most appropriate one is this last one. Given y as a function of x, you just use that formula. So that's what we're going to do. So we compute curvature using that formula. And it's pretty simple. You just compute the first and second derivative of the hyperbolic sine function. The derivative of hyperbolic sine is hyperbolic cosine of x. The second derivative of hyperbolic sine is hyperbolic sine of x. And then the curvature function is the absolute value of the second derivative divided by 1 plus the first derivative, which is hyperbolic cosine, squared, all raised to the 3/2 power. Now we need to keep the absolute value bars on that function because of the nature of the hyperbolic sine function. It is positive sometimes and negative other times. I'm just going to do a rough sketch of the hyperbolic sine function. Hyperbolic sine is defined in terms of this 1/2 e to the x and another function, -1/2 e to the negative x. It's just the sum of those two functions. So if I'm graphing the hyperbolic sine function, it's helpful to graph those two functions first. So 1/2 e to the x looks just like e to the x, it's just 1/2 as tall. Looks kind of like that. And -1/2, so that's, if I distribute that 1/2 here, I'll get a -1/2 out front. -1/2 e to the negative x is like taking that same function, we had the e to the x function, multiplying it by -1/2 is going to make it half as tall, and then it's going to flip it across the x-axis, and then replacing the x with -x flips it across the y-axis. And so what we get is a picture that looks something like this. And those are an excellent guide for graphing this hyperbolic sine of x function. Now when x equals 0, we've got e to the 0 minus e to the -0. The opposite of 0 is 0. So this is just 1 minus 1, which is 0 times 1/2, so we get 0. And then as x goes to infinity, this is e to the x. So if x is really large, e to the x is really large. But if x is a really large number and we've got e to a negative number, which is large in magnitude, this guy is going to approach 0. Because let's think about it. If it's e to the negative 1,000, that's 1 over e to the 1,000. So it's 1 over something really large. So that's going to be really small. So as x goes to infinity, this guy goes to 0, and the hyperbolic sine of x function approaches this curve, 1/2 e to the x. Now it goes to infinity. The limit of hyperbolic sine of x as x goes to infinity is infinity. But I think it's more telling to say that this function approaches this. And it's always just a little bit less than that because this is a tiny positive number as x goes to infinity. And so we end up with a curve that looks kind of like this. And then as x goes to negative infinity, this guy is going to be e to a large negative number, large in magnitude number. So that's going to go to 0. And then we'll have a negative times a negative, which will make this positive. So if x is a large negative number, this is really close to 0. And then this is a really large number. And we're taking a really large number and multiplying by negative 1/2. And so we have a function that goes to negative infinity. But again, more telling is that this e to the x is approaching 0, and the hyperbolic sine function is getting very close to that 1/2 times negative 1 times e to the negative x. So it's getting very close to this function here. So that's roughly what y equals the hyperbolic sine of x looks like. So we need the absolute values because when x is positive, the hyperbolic sine of x is positive. When x is negative, the hyperbolic sine of x is negative. And of course, when x is 0, it's 0. So we need the absolute value there. But that's not a good form for taking the derivative. And we need to take the derivative because of this guy. So let me back up before we talk about how we rewrite this so it's easier to take the derivative. Let's focus on the question. The question says, find the points in the curve at which the curvature is a maximum. In order to find the maximum curvature, we're going to use the first derivative test from Calculus 1. Now, in order to do that, the first thing we need to do is we need to find the critical values of our function. And remember what that means. I don't actually know what that curvature function looks like, but maybe it looks like this. When you're finding the critical values, you're finding the x values but that will give you a slope of 0. So we have a slope of 0 at the top and a slope of 0 at the bottom for all of these. And we're also finding the x values where that derivative is undefined. So this will require finding the derivative, setting it equal to 0, and solving for x. And then you also want to include x values that are in the domain for which that derivative is undefined. Oops, sorry, I'm off the screen. And then once you have those critical values, you have to determine whether they correspond to mins or maxes. We were asked to maximize k. We want to maximize the curvature. We don't want to minimize the curvature. So we need to make sure that we're actually maximizing it and not minimizing it. In order to do that, we need to look at how that slope changes. That's what we do with the first derivative test. If the first derivative changes from positive to negative at a critical value, what we have is a relative max at that critical value. Because if the first derivative is positive, that means the function's increasing. So if we go from increasing to having a 0 slope to decreasing, we're going to be at a max. Or if we go from decreasing to having a 0 slope to increasing, we'll be at a min. And it doesn't necessarily have to have a 0 slope there. The pattern still holds. If we go from increasing to not having a slope to decreasing, and that x value is in the domain, we have a max there as well. So we need to make a sine chart. And that is a sine chart for the first derivative. And then we use the critical values as tick marks on our sine chart, on our number line. And then we're going to see like where that derivative changes sign. If it goes from positive to negative, we know we're at a max. If it goes from negative to positive, we know we're at a min, provided that x value is actually in the domain of the original function. So let's look at this function. Let's first think about the domain. Well, I haven't graphed the hyperbolic cosine function yet, but the hyperbolic cosine function is very similar to the hyperbolic sine function. The hyperbolic cosine function is defined this way. It's 1/2 e to the x plus e to the negative x. So there are kind of like asymptotes right here, where that function gets very close to 1/2 e to the x on this side and 1/2 e to the negative x on this side. When x equals 0, we get 1 plus 1, which is 2, over 1/2, or excuse me, times 1/2, which is 1. And we get something that kind of looks like a parabola, but it's not a parabola. It's actually this combination of exponential functions. So that's hyperbolic cosine. If I take it and I square it and I add 1, it's definitely positive. So this is well defined all the time. And the hyperbolic sine of x is well defined all the time as well. So the domain of kappa, or the domain of our curvature function, is negative infinity to infinity. So keeping that in mind, now if I want to maximize this function, and I'm not maximizing the hyperbolic sine function, I'm maximizing this curvature function, which I found, I've got to do the following. I've got to find the derivative, I've got to set it equal to 0, I've got to think about x values where that derivative is undefined, and then we have to make a sign chart for k prime. Now it actually is quite involved to take the derivative of this. So I'm going to do a little bit of algebra first so that it's written in a different form, a form that's better for taking the derivative. And then we're very carefully going to take the derivative using the quotient rule and the chain rule repeatedly, and then we'll set it equal to 0 and solve for x. And we'll think about where it's undefined as well. Now, there is a rule for the derivative of the absolute value function, but rather than using that rule, I would prefer to rewrite this in a slightly different way. Here's a fact. If you take the square root of a number squared, you might think that you always get that number back, because you think the square root function and the squaring function, they undo each other and you just get the number back. But that's not exactly true. That's true if a is positive. If I take 3 squared, if I take 3 and I square it, I get 9. The square root of 9 is 3. So if I plug in 3 here, I get 3 out. But that's not true if x or a is negative. If I plug in -3 here, -3 times -3 is positive 9, and the square root of positive 9 is positive 3. So if I plug in a -3, I don't get -3 back, I actually get positive 3. So this will always give me not a, but the absolute value of a. This positive square root is always going to return a positive number, except for when it returns the number 0. Okay, so with that in mind, I can take this hyperbolic sine function and rewrite it in this form. It's actually the square root of that hyperbolic sine function squared. But I don't want to write it as a square root because we don't have rules for square roots. But I can rewrite a square root as a rational exponent. There's an implied 2 there and an implied 1 there. The square root of x is actually x to the 1/2 power. And if you're saying, why does that work that way? It's just applying this rule. If you have the x to the n over m, that's the mth root of x to the n. The number in the denominator is the index of the radical. The number in the numerator is that power inside. So that's what I'm using here. So this absolute value of hyperbolic sine of x is hyperbolic sine of x squared raised to the 1/2 power. Now I also want to use another algebra rule to rewrite this guy. Remember, if you take x and you raise it to a power and then raise that to a power, you would just multiply the exponents. You remember how that works? Well, in the same way, we could do that backwards. So this 3/2 power, I can think of as taking this expression and cubing it and then raising it to the 1/2 power. And if you're saying to yourself, why on earth would you do that? It's because of that 1/2 power up there. I'd like to have this to the 1/2 and this to the 1/2, so I can use the following rule. If you've got a fraction raised to a power, you can apply the power to each of those inside. That also works backwards. So if I've got this to the 1/2 over all of this to the 1/2, I can write that as this function to the 1/2. Now, rather than writing this as hyperbolic sine squared x or hyperbolic cosine squared x, I'm going to do something else just a little different here too. That's really hyperbolic sine of x quantity squared. And hyperbolic cosine of x, or hyperbolic cosine squared of x, is the same as hyperbolic cosine of x squared. And I'm writing it that way just to make it a little bit easier to use the chain rule. Okay, so I think this is the right form, in the right form for us to take the derivative. We would use the chain rule here. To get ready to take that, compute that derivative, let's just write down our two rules that we're going to need. I've got a quotient inside a power function. So let's talk about the chain rule first. The chain rule says the following. If I'm taking the derivative of a function nested inside of another function, like this, first I'll take the derivative of the outside function. And then I evaluate it at the inside function. And then I multiply by the derivative of the inside by the chain rule. That's what the chain rule says. So you take the derivative of the outside function, you plug it back in, you don't do anything to it, you just plug it back in, and then you multiply by the derivative of the inside. That's necessary. We're going to do that here. We also have a quotient. We're going to need the quotient rule. This is probably my favorite mnemonic from high school. If I've got the derivative of f over g, my high school AP Calculus teacher showed me the following. He said, if this is the high function and this is the low function, the derivative of high over low is low d high minus high d low over low low, and the d is an operator, so it applies to what's in front of it. That is very helpful when I want to write out the derivative of a quotient. So it's low d high, that's the bottom function times the derivative of the top function, minus high d low. So top function times the derivative of the bottom function over low low, that's the bottom function squared. Okay, so that is our plan. That's what we've got there. And now we are ready to find some critical points. So we're going to apply these two rules in order to find that first derivative of this function with respect to x, and then we're going to set it equal to 0, and we're going to solve for x. And then those critical points are going to populate our sign chart, and then once we've got our sign chart, we will determine where our curvature is maximized. Now this derivative takes so long, it's just such a long expression that I'm going to change my paper to sort of landscape mode. I'm going to turn it sideways so that we can take the derivative of this. All right. So we had a function nested inside of another function. And actually, I should show you again. It's this function right here, and it's raised to the 1/2 power. Now, whenever you're deciding what to do, you want to look at the overall structure of the function first. I see I've got a function to the 1/2 power. So I'm going to use the chain rule, where this is my inside function and my outside function is that power function. Now, if you're saying to yourself, you look at this and you're saying, which one is the inside function? It looks like hyperbolic sine of x could be the inside function, hyperbolic cosine of x could be the inside function, 1 plus hyperbolic cosine squared x, like that's inside this cubing function in the denominator. Which inside function are you talking about? Rather than focusing on that, I want you to focus on the outermost function. We want to do that first. This 1/2 power is on the outermost function here. So we'll start on the outside and we'll sort of work our way in. I'm taking the derivative of a function raised to the 1/2. This is my inside function. My outside function is that 1/2 power function. And this is what we get. We do the derivative of the outside first. And the derivative of the outside is 1/2 times the inside function to the negative 1/2. And then I just put my inside function back in. And I'm writing it this way, again, just to make it easier for us when we use the chain rule in a little bit. That's the derivative of the outside evaluated at the inside. So you don't take the derivative yet, you just plug it back in. And then you multiply by the derivative of the inside with respect to x. Okay. Now, one thing that I will use to simplify this guy right here is another exponent property. You've got a fraction raised to a negative power. So here's a fact. If you have a fraction raised to a negative power, well, that's 1 over the same fraction raised to a positive power, but taking 1 over a fraction is just flipping it. So what this does, when you take this fraction and raise it to a negative power, it just flips it and raises it to the same power that makes it positive. So I can take this negative 1/2 and I can rewrite this. I can rewrite that as the same expression to the positive 1/2 if I flip the numerator and denominator. So I'll have a 1 plus hyperbolic cosine of x squared, all cubed, all divided by hyperbolic sine of x squared. Okay, and then over here, we want to take the derivative of the inside function. And since this is a quotient, it requires a quotient rule, excuse me. So it's low d high. The bottom function times the derivative of the top function. Now that's got a function nested inside another function as well. So this requires the chain rule. So I've got a function squared. The derivative of a function squared is 2 times that function. Plug that function back in, and then you multiply by the derivative of the inside. The derivative of the hyperbolic sine function is the hyperbolic cosine function. So that's low d high. Now we're going to subtract high, which is hyperbolic sine squared. Or you can leave it like that if you want to. Times the derivative of the low function. You can see why I decided to turn my paper sideways. So the derivative of that bottom function requires the chain rule again. Focus on the outermost function. It's that cubing function. Everything else is inside. The derivative of a function cubed is 3 times that function squared. So put the inside function back in, and then you multiply by the derivative of the inside. Now this is a sum. The derivative of the sum is the sum of the derivatives. So you just take the derivative of this piece, and then you add the derivative of this piece. And all of that is a factor multiplying this. So you're not taking this and multiplying by 0, although it's tempting. You're taking this and you're multiplying it by the derivative of this whole thing. The derivative of 1 is 0. And then we're adding the derivative of hyperbolic cosine of x, quantity squared. If this is our inside function now, the derivative of that function squared is 2 times that function. The derivative of x squared is just 2 times x, times the derivative of the inside, and the derivative of hyperbolic cosine is hyperbolic sine of x. Okay, so that's low d high minus high d low over low low. I've got a function cubed. And again, we're going to use that power rule. You got something raised to a power, you just multiply the exponents. So if I'm taking this function cubed and I'm squaring it, because it's that function times itself, I just multiply the 3 by a 2. And I think I'm going to put that exponent on the hyperbolic cosine now. And this squared is that to the 6th power. Okay, so this is our derivative. It's very long, as you can see. We want to simplify this as much as possible. And the way I would do that is I would write this as one large fraction, and I want to factor that numerator as much as possible. So in the denominator, I've got 2 times hyperbolic sine of x squared. Oops, that's actually hyperbolic sine of x squared raised to the 1/2. Remember, that's the absolute value of hyperbolic sine of x. That's where we got that from. And then in the numerator, you've got this raised to a power raised to a power. That 3 and that 1/2 can be multiplied. So I'm going to make that 3/2, and I'm just choosing to use the typical notation for that hyperbolic sine squared or hyperbolic cosine squared function right there. So I've got that, and then this is 1 plus hyperbolic cosine squared x, all raised to the 6th in the denominator. So we're going to be able to simplify those a little bit. So far we've taken care of this, we've taken care of this, and we've taken care of this. Now I want to factor everything that's left here. Now a lot of students think like, oh my gosh, how am I going to factor this? It's actually not that bad. You want to think of this as the difference of 2 terms. You want to think of this as a single term, and this is a single term. And then you want to take out anything this term and this term have in common. Well, I've got a 1 plus hyperbolic cosine squared cubed here, and a 1 plus hyperbolic cosine squared squared here. So that 1 plus hyperbolic cosine squared squared is common to this factor and this factor. So I'll factor that out. Okay, what else do they have in common? Well, this one has a 2 hyperbolic sine of x hyperbolic cosine of x, and this has a 2 times hyperbolic sine of x hyperbolic cosine of x. So we can factor that out as well. Okay, keep going. Then you ask yourself, this times what, or this times what will give me this? Well, that's taken care of, and 2 of those 3 are taken care of there. So what would be left over after we take this out is that 1 plus hyperbolic cosine squared to the 1st. So I just have 1 of those right there. Okay, so that's that. And then I ask myself the same question. This times what gives me this expression? Well, I don't have the 3, I don't have the hyperbolic sine squared. So we've got that. I took out the 1 plus hyperbolic cosine squared quantity squared. That's already been factored out, and then this has been factored out. So since these guys were all factored out, the only thing left was that. Okay, so let's simplify as much as we can. That 2 and that 2 reduce. I've got this expression raised to a power times the same expression raised to a different power, more exponent properties. You're going to add the exponents. And then you have that same expression in the denominator. Remember that, how that works? You subtract the exponents. So this is 1 plus hyperbolic cosine squared to the 3/2 times the same thing to the 2nd. So you just do the 2 plus the 3/2, or 4/2 plus 3/2 is 7/2. And we still have this hyperbolic sine, and I missed my x. All of these functions need x's. They need something inside them. I'm going to group this a little differently. I've taken care of this piece and this piece, so I'm going to put this 1 plus hyperbolic cosine squared to the 6th under this one. So we're going to simplify that in a minute. And then I've got hyperbolic sine of x over this, and I know it's been a little bit, but remember that's actually the absolute value of hyperbolic sine of x. So it's almost hyperbolic sine of x, but this is only going to return a positive number, and that is sometimes positive and sometimes negative. Okay, so that took care of this piece and this piece and this piece. Okay, what's left? I've got the hyperbolic cosine function there, and then I've got this factor. Well, this factor can be rewritten using an identity involving the hyperbolic functions. Now, this is definitely not something that I would expect anyone to remember from Calculus 1, but when you are working on a problem involving hyperbolic functions, it's perfectly reasonable to expect that you would have to look up some identities. So later I'm going to set this equal to 0 because remember, I think I labeled this incorrectly, that's k prime. Later I'm going to set this whole product equal to 0 and then solve for x. So I want to write this in a form that will make it easier for me to solve for x. And right now I can't really solve it for x because I've got hyperbolic cosines and hyperbolic sines in the same expression. So what we would typically do is what we would typically do in trig class. We would try to get everything in terms of one of those functions. Well, then there's an identity. There's an identity, excuse me. We've got hyperbolic cosine squared x minus hyperbolic sine squared x. That turns out to be 1. You probably proved that in Calculus 1. It's almost like sine squared plus cosine squared equals 1, but it's just different enough that your intuition is wrong. But yeah, this is the hyperbolic identity involving hyperbolic cosine and hyperbolic sine. Using this, I can solve for hyperbolic cosine in terms of hyperbolic sine, just by adding this to both sides. Okay, so this hyperbolic cosine squared x can be rewritten as 1 plus hyperbolic sine squared x. All right, so I took care of all of these factors except for this one, and the last one can be simplified in this way. 1 plus 1 is 2. Hyperbolic sine squared minus 3 of those is going to be minus 2 of those. And we're here. Okay. So now we want to take this first derivative and set it equal to 0 to find the critical points. Now, this expression can be simplified further. It's 6 we can think of as a 12 over 2. This is going to give us that 1 plus hyperbolic cosine squared to the 5 over 2 in the denominator if we simplified it. That's really not too much of our concern, because when I'm solving this, I'm solving for x. There are only a couple of things I need to worry about. I need to find the x values that would cause division by 0. That would make this k prime undefined. And those are going to be critical values. And then I also need to find the x values that make this equal to 0. Well, hyperbolic cosine of x, remember how that looks. It looks like this. In that denominator, we're supposed to square this positive number, because all the y values on this graph are positive. Take those positive numbers and add 1 to them, and then raise it to a power. So this is never 0. So we're good there. And then you've got this function. Now this is a function divided by itself. Well, this is going to be two different things depending on whether x is positive or negative. When x is positive, hyperbolic sine of x is also positive. And when x is non-negative, when it's greater than or equal to 0, hyperbolic sine of x is greater than or equal to 0. So that means that absolute value of the hyperbolic sine of x is just equal to itself when x is positive. Or to be as inclusive as possible, when x is non-negative. When x is greater than or equal to 0, this is equal to itself. But when x is negative, hyperbolic sine of x is negative. Remember that graph? It looked kind of like this. There were some asymptotes or something that was sort of like an asymptote, and it looked like this. In this case, when I take the absolute value of hyperbolic sine of x, I'm going to take this number. Maybe it's -3 over here. and I'll multiply it by -1 to make it positive. So this is negative hyperbolic sine of x when x is negative. And that means that when I take hyperbolic sine of x and I divide it by the absolute value of hyperbolic sine of x, well, when hyperbolic sine of x is positive, that happens when x is positive, we just get a number divided by itself, so that's going to give us a 1. When x is 0, we'd be dividing by 0, so we can't do that, so that's not in the domain of this function. And when x is negative, the absolute value of hyperbolic sine of x is the negative of that. If you're saying, how is it negative? Remember, this is a negative number. A negative times a negative is a positive, and that's giving us the positive value of that absolute value. So this is going to be a -1 in that case. Okay. So now we know this factor is undefined when x equals 0. So x equals 0 is one of our critical values. And that's because k prime at 0 is undefined. And then you've got this over here. Hyperbolic cosine of x over 1 is never 0. Remember, it's always greater than or equal to 1. That's what our graph is. The y values are always larger than 1. So this is never 0. We have a problem with this one when x equals 0, because that is undefined. This is never 0, but this function could be 0. So when we're setting k prime equal to 0, so this is k prime, when is it 0? Well, it's 0 when this is 0, when this is 0, when this is 0, or when this is 0. That's never 0. That's never 0, but it's undefined at x equals 0. That's never 0. The only time k prime could be 0 is if this last factor equals 0. We're almost done getting our critical values. So we'll say k prime of x equals 0 when 2 minus 2 times the hyperbolic sine squared of x equals 0. So that means 2 equals 2 times the hyperbolic sine squared x, which means 1 equals the hyperbolic sine squared of x. If I'm trying to get x by itself, we'll take the square root of both sides. That'll lead to a plus or minus on this side. And we get this. Okay. Now, solving this equation might seem to be hard because we don't really know what hyperbolic sine or how to define hyperbolic sine. You might say, well, I can use the inverse hyperbolic sine to get x by itself, but would that even really help me? It turns out that's one way of doing this. In order to get x by itself, we could take the inverse hyperbolic sine of both sides. And the inverse hyperbolic sine of the hyperbolic sine of x just gives me an x. So x is equal to the inverse hyperbolic sine of 1, or x is equal to the inverse hyperbolic sine of -1. Those are two possibilities. But you might think, well, what is that? And what is that number exactly? So we're saying y equals 1 on this sine function, or y equals -1 on this hyperbolic sine function. And the question is, what are the two x values that go with those y values? I'm looking here. If hyperbolic sine of x equals -1, what is that x value? Or if hyperbolic sine of x equals +1, I'm asking, what is that x value? So I want this guy or this guy. You could just write your answer this way, and sometimes the computer will like it and sometimes it won't. Or you can remember what hyperbolic sine of x is in terms of exponentials. So let's do that. The hyperbolic sine function is 1/2 of e to the x minus e to the -x. And we're setting that equal to plus or minus 1, and we're solving for x. So the first thing I would do if I want to solve this for x is multiply both sides by 2. And I think I'll take that negative exponential and write it as 1 over the same thing but positive. So we've got that there. And this is because I'm using this fact. We've got x to a negative power, that's 1 over x to the same power but positive. It works the same with exponentials as it does with power functions. Okay, and now we're trying to solve these two equations for e to the x. So what I would recommend you do in order to get rid of this fraction is multiply both sides by e to the x. You've got e to the x times e to the x over here, which can be simplified using exponent properties, but I'm not going to. I'm going to write it like that. And then you want to distribute this here. That e to the x divided by e to the x is 1. And then you've got a plus or minus 2 times e to the x on this side. I'm going to write this as two separate equations now. We'll focus on solving each of them separately. And I'd like to subtract that 2 e to the x from both sides. You'll see why in just a moment. And on this one, let's add the 2 e to the x to both sides. Now you might recognize these from pre-calculus. This is quadratic in form. It's not a quadratic equation, but if I let u equal this, if I let u equal e to the x, that's u squared minus 2u minus 1. And over here we've got u squared plus 2u plus 1. If we write these as quadratic equations in terms of u, and then we back substitute to solve for x, we could find the x values that make this equation true. So let's do that. We'll have u squared minus 2u minus 1 equals 0. And over here you've got u squared plus 2u plus 1 equals 0. And we're solving these for u. Well, I think I will complete the square on this. I'm going to add the 1 to both sides. I'll subtract 1 from both sides here. Oops, that was supposed to be a minus 1 to begin with. I'm adding 1 to both sides here as well. So I end up with u squared minus 2u equals 1, and u squared plus 2u equals 1. And we're solving these for u. I'm going to complete the square. So the number in front of u is b. Take half of that. It's negative 1 and square it. Negative 1 times negative 1 is positive 1. So you want to add that to complete the square on that side, and make sure you add 1 to the other side to compensate. You want to make sure you do the same thing to both sides. The same thing is going to happen over here. B is just positive 2 instead of negative 2. Okay, so on this left-hand side here, I've got this expression, which can be written as u minus 1 squared equals 1 plus 1, and 1 plus 1 is, of course, 2. And this factors to u plus 1 squared, and 1 plus 1 is 2. And we're trying to get u by itself. So take the square root of both sides. Don't forget the plus or minus on the side with the number. And you get u by itself by adding 1 to both sides. Oops, on this one. And subtracting 1 from both sides on this one. Okay. Now, I want to solve for u, or not solve for u, excuse me, I want to solve for x. Remember, u was just something we made up so we could solve this equation. U was e to the x here and here, and u was e to the x there and there. So I'm going to replace u with e to the x. And then I'll write this as two different equations. I've got e to the x equals 1 plus the square root of 2, and e to the x equals 1 minus the square root of 2. Now this one I can solve. This one doesn't work though. That's a 1 minus square root of 2. Square root of 2 is larger than 1, so this is going to be a negative number. And e is never equal to a negative number. Remember what that exponential graph looks like? It looks like that. The y values on the exponential are always positive, so that's not going to happen. To get rid of the e, we take the natural log of both sides. And we get x equals natural log of 1 plus the square root of 2. Same thing over here. Let's let u equal e to the x, so you back substitute. And this corresponds to two equations. You've got e to the x equals negative 1 plus the square root of 2, and e to the x equals negative 1 minus the square root of 2. Well, that never happens because e to the x is never negative. Square root of 2 is larger than 1, so this is a positive number. So we can solve this by taking the natural log of both sides. It's the inverse function for our exponential, so it goes undo each other and we just get x back. And that's our other x value. That was a lot of work. Okay, what were we doing again? Remember, we were asked to find the points on the curve at which the curvature is a maximum. So we had to find this curvature function and to do a little rewrite so we could take its derivative. And then to maximize this function, we have to use the first derivative test. So the first thing we needed to do was find the critical values. And the way we do that is we take the derivative and set it equal to 0 and solve for x. And also find any x values in the domain for which k prime is undefined. Well, k prime was this, and k prime is undefined when x equals 0, because we've got that right there, which is 1 half of the time and negative 1 the other half of the time. And then we said, when is k prime equal to 0? Well, k prime is equal to 0 when this is true, which is when this is true, when x equals these values. But if you're saying, what is the inverse hyperbolic sine anyway? It's actually this thing in terms of logarithms. So we actually found two x values that are critical values for our chart. So k prime equals 0 when x equals the natural log of 1 plus the square root of 2, and x equals the natural log of square root of 2 minus 1. Okay, so we're not done yet. We need to find out when the curvature is maximized. This just tells us curvature is 0 here and 0 here, and curvature is undefined at x equals 0. Okay, so let's make our sine chart. Sorry, this is such a long problem. Actually, I'm not sorry that it's a long problem. Just takes a long time. Thank you for your patience, and like this is the process. This is how you find out where the curvature is maximized. So let's write down k prime. And there's a number line. These are x values. X goes from negative infinity to infinity because the domain of our curvature function was negative infinity to infinity. And the critical values were x equals 0, x equals the log of 1 plus the square root of 2. So let's figure out what that is. It's approximately, sorry about that reflection, 0.881. And then there was the other one, the log of 1 minus square root of 2. Oh wait, no, it was square root of 2 minus 1. Sorry about that. And that's a negative 0.881. So there's some symmetry there. And if you're confused now because you see that log and you see a negative, just know that the logarithm function looks like this. This is y equals natural log of x. The input values have to be positive, but the outputs can be negative. So it's perfectly fine to have a log of negative 0.881. The y values on this graph are negative when x is less than 1. When x is some number between 0 and 1, we get negatives. Okay, so these are the critical points, and k prime was this. It was hyperbolic sine of x times hyperbolic cosine of x times 2 minus 2 times hyperbolic sine squared x, all divided by 1 plus hyperbolic cosine squared x raised to the 5/2 times the absolute value of hyperbolic sine of x. So that's that. We can write it that way, or we can write it this way. I think I want to write it this way. I want to think of each of these factors separately. And then we've got the 2. And of course, you could have factored out a 2 as well. I just chose not to. So K prime is this times this times this times this. I'm going to make my sign chart down here again. Okay. And that's to the 5/2. I forgot that 5/2. Well, hyperbolic cosine is always positive, so this is going to be a positive number. Oops, forgot that h. It does not matter what x is, this is positive. So we're going to have positive, 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 and positive, no matter what x interval we're on. So K prime is a positive times this, which I know is a little bit ago. That's a positive 1 when x is positive, and a negative 1 when x is negative. So over here, it's going to be negative, and over here, it's going to be positive. Okay, then the hyperbolic cosine function. It's always positive. The y values on that graph are always greater than 1, greater than or equal to 1. And then this is the only one where we might actually have some sort of interesting sign differences. I factored out the 2 to make it a little bit easier on us. So that is 2 times the quantity 1 minus hyperbolic sine squared x. And remember, this is about negative 0.881, and this is about positive 0.881. Okay, so let's do that. Let's just pick on this interval. You can pick any x value you want and plug it into the factor. Let's just choose negative 1. So we'll have 1 minus, and I would like to use hyperbolic functions. Isn't that nice? The calculator has those. So I want hyperbolic sine of negative 1. I actually want that whole thing squared. So I'll put some parentheses here and a paren there, and I want to square that. And I get a negative value. Okay, so now I want to pick an x value between negative 0.881 and 0. So we'll do, let's just do negative 0.5. So I have 1 minus the hyperbolic sine of negative 0.5, but I need to square that. So that's positive. And you're multiplying it by positive 2, but that doesn't change anything. Let's use positive 0.5 on the other side. Well, actually, I think we can see, well, no, it's not obvious. There are some properties of the hyperbolic functions that we could apply here, but most of us have forgotten them, so we won't apply them here. I want to plug in x equals 0.5, so I'm going to open parentheses, hyperbolic functions. I choose number 1 for hyperbolic sine, plug in 0.5. Oops. You want to square that. And that's a positive number. And then over here we have 0.881, so let's plug in hyperbolic, or let's plug in x equals 1 over here. So you have 1 minus, open parentheses, hyperbolic sine of 1, quantity squared, and that's a negative 0.38. If you notice the symmetry, that's just because the hyperbolic sine function turns out to be an odd function. Okay. All right, so if I want the sine of k prime is this times this times this times this. So two negatives become positive when you multiply them. And then on this interval, k prime is a positive times a negative times a positive times a positive, which would make that negative. And then it's the product of 4 positives here and the product of 3 positives and a negative here. Okay, so that means the curvature is increasing on this interval. Then we have a 0 slope at the top, and then it's decreasing over here. And then it's decreasing, and then the curvature is undefined, and then it's increasing. And then over here, it's going from increasing to having a 0 slope to decreasing. We're looking for maxima. So if it goes from positive to 0 slope to decreasing, or if the first derivative goes from positive to 0 to negative, or if the function goes from increasing to 0, having a 0 slope to decreasing, we have a relative max here. We have a relative min here, but it's undefined, so maybe a sharp corner. And then over here, the function goes from positive to having a 0 slope to decreasing. That's the original function, not k prime, but k itself has this behavior. So we're going to have a relative max here, and a relative max here, and a relative min at 0. And we wanted to maximize those two. It has a relative max at x equals natural log of the square root of 2 minus 1, and x equals natural log of 1 plus the square root of 2. Okay, back here. It says find the points on the curve at which the curvature is a maximum. The x value is, well, it says the smaller one first. That's the square root of 2 minus 1. Natural log of the square root of 2 minus 1. We need to find the y value there. And over here, x is 1 plus the square root of 2, the log of that. So to find the corresponding y value, we can substitute these x values into the original function. Say when x equals natural log of the square root of 2 minus 1, y equals the hyperbolic sine of that. Now this is easier to simplify if you write it in terms of exponentials. So this is 1/2 of e to this power minus e to that same power but negative. I know it's a little weird. Okay, so in order to simplify this, the log and the exponential, they undo each other. So we just get a back. And over here, you can't just cancel the log and the e because you have a coefficient out front. You have to use this property. Bring that power inside, and you get that. So I'm going to bring that -1 power inside. So this ends up being 1/2 times the square root of 2 minus 1 minus, and then those are going to undo each other, this expression to the -1 power, which is the same as that expression to the +1, but in the denominator. I know, it looks very tedious, doesn't it? But now you're like, okay, I want to get a common denominator. So let's make the square root of 2 minus 1 our common denominator. So you have 1/2 times this, and here you FOIL. First times first is the square root of 4, which is 2. Outer times outer is the square root of 2, or negative square root of 2. Inner times inner is the same, so you've got 2 of those. And last times last is a +1. And that's your numerator there, and then you're just going to subtract that, and you keep the common denominator. So those guys undo each other. And you can factor out a 2. So you've got, actually, let's factor out a -2. So if -2 times -1 is that 2, and -2 times positive square root of 2 is that. And all of that is divided by square root of 2 minus 1. While square root of 2 minus 1 and -1 plus square root of 2 are the same thing, and we get -2 divided by 2, which is -1. Oh, actually, we said when x equals this, hyperbolic sine of x equals -1. So that means our ordered pair is this. Do you remember that -1 from earlier? It's okay if you don't, but there was actually an equation that we solved. It was like hyperbolic sine of x equals 1, hyperbolic sine of x equals -1. It was a long time ago. It's been a long video. This was hyperbolic sine of x equals plus or minus 1. On this one, when I took the positive 2 times the e to the x here, that came from the positive 1. And this where we had the -2 times e to the x, that came from the -1. So remember, this original equation was hyperbolic sine of x equals plus or minus 1. So this one was equivalent to hyperbolic sine of x equals 1. And this one was equivalent to hyperbolic sine of x equals -1. So what we just said was when x equals this value, which was at approximately -0.881, hyperbolic sine of x equals -1. So that tells me I don't have to do all the work for the second one. If I plug this in for x into the hyperbolic sine function, I should get 1 back. I'm not actually going to check that one. But if you want to, you can by doing all of this, writing the hyperbolic sine in terms of exponentials and using the properties of exponents and logs to simplify. That's our x value, and the y value that goes with it is positive 1. Okay. So this was y is -1 here. Remember, that's what we were trying to solve. And then y is positive 1 there. Okay. Almost done. The last part says find the limit of kappa or k or the curvature as x goes to infinity. So we're looking at the limit of this as x goes to infinity now. And we did rewrite this earlier. We rewrote it in this form. Okay. Now, I claim that if I've got a function inside a square root, and that's what that 1/2 power is, that this function, oh, actually, no, I can't do that. So never mind, I was doing something else. We're taking the limit as x goes to infinity now. The numerator goes to infinity and the denominator goes to infinity. Hyperbolic sine of x squared, that's gonna get really large, and hyperbolic cosine is gonna get really large. We're gonna square it, we're gonna add 1, and then we're gonna raise it to the 3rd power. And then we're going to take the square root of all that, but this is a large number over a large number. So this is an infinity over infinity indeterminate form. Okay, so with an infinity over infinity indeterminate form, I guess we could use L'Hopital's rule next. Let's see, we'll do the derivative of the numerator over the derivative of the denominator. And now I'm just applying that 1/2 here and here. And actually, I'm not applying L'Hopital's rule yet. Since x is going to infinity, hyperbolic sine of x is definitely positive there. So this function that's being squared and then we take the square root, it's just going to give us hyperbolic sine of x back. Because x is positive. It's the only reason we get to assume that. Okay, we still have an infinity over infinity indeterminate form. But let's use L'Hopital's rule. Take the derivative of the numerator and the derivative of the denominator, and they're going to have the same limit. For the derivative of the denominator, we use the power rule. This is your outside function, and the inside function is this 1 plus hyperbolic cosine squared x. So the derivative of the outside is that power times the inside function raised to the 1 less power. So I've got 1 plus hyperbolic cosine squared x inside here, times the derivative of the inside by the chain rule. The derivative of 1 is 0, and the derivative of hyperbolic cosine squared x needs the chain rule as well. So I've got hyperbolic cosine raised to the second power. Derivative of something squared is 2 times that something times the derivative of the inside by the chain rule again. And that 2 reduce, and this hyperbolic cosine and that hyperbolic cosine reduce. And so we've got this, the limit as x goes to infinity of 1 over the square root of 1 plus hyperbolic cosine squared x times hyperbolic sine of x. And this is not an indeterminate form anymore. This is getting large, so you square it, you add 1, you take the square root, it's still large, and this is getting large. 1 over a really large number is a really small number. So that limit is 0. So this was a long problem, and it reviewed a lot of different things. How to solve equations that are quadratic in form, the first derivative test, hyperbolic functions, all of that. So I thought it was a pretty interesting problem, but this would probably be a little too much for, let's say, your final exam. But remember what we were asked to do. We were asked to find the points on the curve at which the curvature was a maximum. So we found that curvature function, and we used the first derivative test to maximize it. That required taking the derivative, which was this, and we had to turn the paper sideways, and then thinking about where the derivative is either 0 or undefined. And it's 0 when this is 0. Took a lot of work to figure that out, but when this turns out to be 0 when x equals one of these logarithms. And it's undefined when hyperbolic sine of x is 0. So we found our critical values. We put those on a sign chart. And then we looked at k prime as the product of these 4 factors. And we found the sign of each of those factors on each of those intervals, and we multiplied the signs to get the sign of k prime. And then we said, by the first derivative test, since k prime goes from positive to negative here, we have a max. Since k prime goes from positive to negative here, we've got a max there as well. And then for each x value, you need to find the corresponding y value, which you can do directly by substituting that x value into the function, and then simplifying using the properties of exponents and logs. Or you could remember the equation where that x value came from. We said, when is the hyperbolic sine of x equal to -1? And that was the solution. And then for the other one, we said, when is the hyperbolic sine of x equal to +1? And that was the solution. So we found the ordered pairs that way. And then the last thing we did was we took the limit of that curvature as k goes to infinity, or as x goes to infinity, excuse me, and we had to use L'Hopital's rule. Now, so what does that mean with my original function? What we're saying is at x equals that logarithm and x equals that logarithm, those are the x values when that curvature is at a maximum. And then after that, actually in between, let's look at our sign chart. From 0 to that point, the curvature is increasing, so it's getting curvier. And then the curvature is decreasing until it decreases to 0. So it's very, very flat out there. over here, curvature is positive, and then it gets to its maximum positive value here, and then it starts decreasing. And at 0, it says it's undefined. The mathematics says it's undefined, but it looks like it's well-defined, but maybe it's just my picture is not a very good picture. Curvature is supposedly undefined at 0, given our definition of this derivative. So yeah, all of this, all that we've done has a physical meaning. Curvature is maximized here and here, and as x goes to infinity, that curvature is approaching 0, which means it's going to be really flat. It's going to be almost like a line as x goes to infinity.